Welcome back, Python family. This is the Python Made Easy series. This is the second class in a series on Python functions. This class is all about the very important topic of scopes. So here we start to talk about scope. When we use a name in a program, Python creates, changes, or looks up that name in what's known as the namespace. In computer programming, namespace is a place where names live. Scope refers to a given namespace. So the location of a name's assignment in our source code determines the scope of the name's visibility to our code. That is, what parts of our code can see it and hence make use of it. Names in Python spring into existence when they are first assigned values, and they must be assigned before they are used. Because names are not declared ahead of time, Python uses the location of the assignment of a name to associate it with or to bind it to a particular namespace. So, the place where you assign a name in your source code determines the namespace it will live in and the visibility of its scope. By default, all names assigned inside a function are associated with that function's namespace and no other. So, if it's assigned within the def, that is the function definition, it can only be seen by the code within the def. You can't refer to it outside the function. There will be no name collision with those variables with the same names outside the function. So the scope of a variable, where it can be used, is a function of where it's assigned. Keep these definitions handy. A variable assigned inside the def is local. A variable assigned to the enclosing def is non-local to nested functions, and variables assigned outside the def are global to the entire module. Functions define a local scope, and modules define a global scope. The enclosing module is a global scope or namespace assigned at the top level of the module file. When you hear global, think module or file. The only way to use a global name outside of the file in which it's defined is to import it. Assigned names are local unless declared global or non-local through the use of their keyword statements. If you need to assign a name that lives in an enclosing def, you can do so by declaring it a non-local statement. And we'll see examples of this in just a short while. Each call to a function creates a new local scope. That is, a new namespace is created each time a function is called. The local scope corresponds to a function call. So each active call receives its own copy of the function's local variables. If you assign a name in any way within a def, it will become local to that function by default. Let's talk about the LEGB rule. When you use an unqualified name inside a function, that's one that you don't preface with, say, a class name or a module name, Python searches up to 4 scopes in this order. L is for local, E is for the enclosing or nested function, G is for global, and B is for built-in. It stops the first place the name is found, so that is the first occurrence wins. When you assign a name in a function, Python always creates or changes the name in the local scope, unless it's declared global or non-local in that function, and we'll get to that. When you assign a name outside any function, the local scope is the same as the global scope, so the module's namespace. And then for comprehension variables of any type, list, dictionary, set, etc., all are local to the expression itself. This all has to do with the variable that you think you're using is the one that you're actually going to use in your calculation. If not, your code could have some pretty unpredictable results and, in fact, be very buggy. Okay, so here's an example. We have defined a function called func, F-U-N-C. It takes one argument, y. X is defined in the global scope, and y and z are defined in the local scope. We return z. At that point, the function ends. But to get this all started, of course, we need a caller, and that is nested in our print statement. Print func 25 is what we pass it as an argument. So func is global because the def statements assign a function object to the name func at the top level of that module. So that's in the global namespace. Y and z are local and exist only while the function is running because they're in the body of our function. The name segregation scheme is in place because local variables serve as temp names that you need only when the function is running. So just at runtime. They are removed from memory when the function call exits, and the objects they reference may be garbage collected if they're not used elsewhere. So let's look at this live. Okay, let's take these concepts and look at some code and see how we can make them real. So we have two snippets of code. Example number 1, example number 2. They're almost identical. We have a function, def, func. It takes one parameter, y, in both cases. In the first one, we have x equals 50 defined in the global space. We have that same one down here, except that we have x equals 100 defined local to the func variable. So this should override this x. So if we're going to pass in the argument 25, which will equal y, then this should add up to 75. But here, this is going to override this 50 in the global space because we'll follow LEGB, local, then enclosed, then global, then built-in. So it stops with the first one that satisfies, and that's local. So this should be 25 plus 100 is 125, and here should be 25 plus 50 is 75 when we run it. Let's see. Save it, F5 to run. And yeah, we get 75 for example number 1 and 125 just as we suspected. So folks, I wanted to give you just another tool in your tool bag. The built-in scope is just a module called built-ins. We talked about the LEGB. To be able to see it, you have to import built-ins like I did here, and then you can do a dir on built-ins as we've done in so many of the other modules before to kind of give us information. The names in the list are divided in two halves. The first half are built-in exceptions, and the second one are functions. And you can do a built-in dot sorted or a built-in dot open or any one of these to be able to tell what type it is. So I encourage you to go ahead and take a look. With what we just saw in built-ins, let's talk a little bit about overriding. Because of LEGB procedure, names in the local scope take precedence and may override the global or the built-in scope names. You need to be aware of this. So we have here, we've defined override me, and then declared a variable open equals foo, and then open, and we try to use open like we would to open a file and pass it data.txt to read it. This open is no longer the built-in, so it'll not work. It'll not be able to open files. So you need to be aware of that. That's one of the things that scope is very important for. Again, you don't want your code to behave in a way that's not expected. Okay, let's look at some more examples. So we're going to start in the upper left-hand corner. We have def equals func. We pass it x. Then we have x in the body of our function, and we return x. Then our caller says func 10,000. It passes 10,000 for x. There is no value set until it's set in the global space during the call. So this is an easy one. It takes 10,000 and it just prints it out for us, right? That becomes the value of x. So that one's pretty straightforward. Now let's go to the one just below it. X equals 52 in the body, and we return x. When we call, we pass it 10,000. So the caller sets x to be 10,000, but when the function is called and run, it's overwritten by the x in the local space. Remember, 10,000's in the global space, right? 52 is in the local space. Local always wins. Let's go to the middle top. This, x equals 5 in the global space, and then our same function with x equals 52. We return x. So func sets 10,000 to be x. However, when it prints out, once again, 52 wins for the same reason we just said before. 52 is in the local space. 10,000 is in the global space. The one below it also prints 52. This time we don't pass anything in, but it's not going to see x in the global space. It's going to see x equals 52 in the local space. So that's what prints out there. Now let's go to the top right. This prints out 5. Why is that? The name x on the outside of the function has nothing to do with the x on the inside of the function. They're two completely different objects. And if we were to do an ID on each, we'd prove that. Func is set to return 52 because that returns the value of what's in the local space, the x that's in the local space. But what we're printing the x in the global space. So that's 5. Nowhere are we printing what's in the function. So we don't say print func and then pass it something like 52 or 100 or whatever. So that's why it's printing what we have here. And this could be an example of something that comes up in some coding test, maybe for employment or something like that. But really think through this. Where am I printing out the value of what's in the function? I am not. So print X, that's in the global space. That print statement's in the global space, and all it sees is the X in the global space, which is 5. So take a look at that and slow it down and send me questions if you have them. Play with it in idle too. That's always a great way to drive it home, even in debug mode. So here this also prints out X, and then it prints out 52 because we're actually calling the function this time, right? The print X, same as above, is in the global space, and it prints out X equals 5 right before the function. But then we actually call the function and print that out, right? Before we just had func, right? But we didn't print it out. We were calling it, but we weren't printing that out. So it was never going to see what was in the body. But here we do that in this very last example, and we actually get 52. So we get 5 for the first print statement, and then 52 for the second. Hopefully that makes sense, guys. If not, let me know. I'm happy to go over it again. Now, as promised, here's where we get to the global statement. The global statement and the non-local are like declaration statements in Python. They are namespace declarations. The global statement tells Python that a function plans to change one or more global names that live in the enclosing module scope or namespace. Global names are variables assigned at the top level of an enclosing module. Global names must be declared only if they are assigned from within a function. Global names may be referenced within a function without being declared. So global allows us to change names that live outside a def at the top level of the file. Okay, let's see this live. An example of what we were just talking about. So we have 2 snippets of code here. This one where we're not using a global within the body of our function, and another where we do. So we'll look at the one that would be more conventional. We have X equals 10 in the global space. Then we have our function globs. X equals 100. We return X. When we call globs, our function, passing no parameters, obviously it doesn't call for that, it's going to return 100. And here, when we print X in the global space, that has nothing to do with globs, that should return 10, right? So let's verify. 110. Okay, now let's comment out this guy. Let's bring this guy to life. Now, what's different here? It's the same thing with the exception of we do declare X global within the body of our function. So this time, we would expect that when we print out the function, it will still be 100. Nothing changes because that returns X, and X is set here to 100. But now when we print X in the global space, this would change X to be the value of 100. The global statement should do that. So we should print out, instead of 110 this time, 100 here, and 100 for the global X. And it does that. Okay? So if you have any confusion about what this is doing or how this is doing it, let me know and I'll try to clear it up as best I can. So let's talk about scopes and nested functions. Enclosing scopes are sometimes called statically nested scopes. Just like if in a function X is declared global, it changes the value of X defined at the module level, what we just saw. If X is declared non-local within the function, it changes the name X in the closest enclosing function's local scope. Here, in this example, the nested def, F2, we're calling it F2, runs while a call to F1 is running. F1 generates a function and assigns it the name F2. So that means F2 is a local variable within the F1 scope. F2 is like a temp function that lives only during runtime or execution and is only visible to code in the enclosing F1. When F2 prints X, it's referring to the X that's living in the F1 namespace. Because functions can access names in all physically enclosing def statements, the X in F2 automatically maps to the X in F1 following the LEGB rules. Right, so it doesn't go as far as the 99. That's at the module level, right? That's in global. X equals 88 is in enclosing with reference to F2. So that's the one it grabs, right? It stops after the first one we see. Now, Here's a question for you. If we comment out F2 as we do in this bottom piece of code, what returns when this code runs? Think it through before your eyes go any further down on the page. Well, the answer is nothing, because the printx statement never gets called. If we never call F2, then what's inside F2 never gets executed, right? We need a caller. We still need a caller. And even though we call F1, that's not good enough. Let's move into the wonderful world of factory functions. Here we see code from the previous slide. It's just written in a more typical way. Let's go to number 1 here, red ball number 1. The def F2 is just like the x equals 88 in that it's something that gets defined within the F1 function. Then in F2, when it says print x, it of course, using LEGB, stops when it finds the x in the outside function. The return F2 statement belongs to F1, but of course it returns what's happening in F2, which is the printing of x. Then we assign the name action as a variable to represent the execution of F1 and all that goes with it, which includes the printing of x. And finally here in number 5, action, our variable, can now become action of function due to its assignment to F1. So we can call it as action. And when we call it, we get the result we would expect, which is 88. It returns the value of x. This type of behavior may be called as a closure. This describes a functional programming technique, or a factory function. This describes a design pattern. So the same thing, just representing 2 different constructs. The main thing to take away is the function object F2 remembers values in enclosing scopes, F1 in this case, regardless of whether those scopes are still present in memory. In effect, they have attached packets of memory, aka state retention, which are local to each copy of the nested function created, and often provide a simple alternative to classes for this particular application. All right, and we'll finish up this module with just a bit more on nested functions. So here we have a nested function called action inside a function called maker. So F is assigned to the call of the outer function maker with an argument of 2. That's representing parameter n. So 2 represents n. Then F, which equals maker2, is passed the value of 3 for the variable of x. So we have F. So now maker is able to return action with a value of 3. So we have maker2 action 3 for 3 to the power of 2, which brings back the value 9. Function action remembers the integer 2, variable n, from function maker, even though maker has returned and exited by the time action is called. Therefore, n is retained as state information attached to the generated action function, which is how we get back its argument squared later when it's called. And if you look on the right-hand side, in this example, we assign new values for both n and x, and it works just the same as in the previous example. But what we're showing here is we can still go back to the original values of 2 and 3 from before, and that still works. Why is this? That's because each call to a function factory gets its own set of state information. Enclosing scopes are often employed by the lambda function generator expression, as you see in this example here. We have maker again, and then we have return lambda x and x to the power of n. So we do the same thing. H equals maker 3, and we pass h the value of 4. So n equals 3, x equals 4. So x times x times x, or 4 times 4 times 4, brings back 64. Well, thanks for joining us on this one, folks, and I hope it helped you. And if it does help you, please help me to help other folks. And you can do that very simply. Subscribe to the Yogi Coder account, and then like this. And if you feel moved to, maybe you share it in some of the circles that you walk so that I can reach more people. If you have any questions, if you have any comments, please leave them below, and I'll see you in the next one.